Welcome, dynamics students, to our last lecture for rigid body planar motion kinematics. And in these two examples in this lecture, we're going to look at more cases of rolling, and we're going to include a little bit of relative reference frame, relative acceleration, and then also look at a case of just pure rotation. Really leverage our expression for sum of the moments is angular acceleration times moment of inertia, polar moment of inertia. Okay, so we're going to start with a combo. We've got, in this case, I'll blow up this little figure here. We've got some surfaces, some which we are going to consider to be a fixed reference frame. So this is like the floor, or some fixed surface. Then we've got a plate with some center of mass kind of right in the middle, and a force is going to be applied to that force P that's going to pull it sideways. It's got its own mass, capital M. The frictional force between the plate and the surface is negligible, so we'll call it, mu2 is approximately 0. On top of the plate we've got like a pipe, and we're looking at this in cross section, so we're just seeing the cross section of the pipe. It goes back into the page in its length. And it's got a mass little m, it's got a radius of little r, obviously center point is at the center of the pipe, and it's got some fixed starting point of its center of mass relative to the wall here. We don't want it running into, I guess. And what we want to do is relate the force that we can apply to this plate, slipping it sideways, to the onset of slip. Right now, as we move this plate over, if we've got enough friction, the pipe is going to roll, and so the pipe might roll off the back. We're assuming maybe it's supposed to do that. Maybe this is some kind of pipe conveyance where we want the pipe to roll off the back. Well, we don't want it to slide for whatever reason. So we're again looking for some kind of criteria of slipping, some criteria of motion that we don't want to have happen. So again, we're going to be looking for some characteristic of the frictional force through mu1 and this force P. And of course, P is being applied to a different rigid body than our cylinder. And the only way that we can connect these two, other than the normal force in what is the vertical direction, is if we have rolling, then we know we have a point of common velocity at that invariant point. But otherwise, the two, we're going to have to relate them some other way. But in the meantime, we can continue with what we do know. So because we're talking about forces, as well as motion, we're going to start with FBDs. And as an aside, since we're pretty darn sure we're going to want to relate something about the moment applied to that pipe, we're going to quick draw our polar moment of inertia of the pipe cross section right here while we're drawing the FBD. We look this up for a thin-walled pipe. We know that we have a polar moment of inertia about the center point, 2 pi times the radius of the pipe times the pipe thickness if it's really small. And we can express that in terms of the pipe's mass per unit length, and we get an expression of our polar moment of inertia of the pipe is r squared m. So it's pretty simple. So we have that ready to go to get an expression for angular acceleration as soon as we have a net moment, which we'll have pretty soon. So we've got our FBD of the pipe, we've got the weight pulling down, which we can apply at the center of mass. We have the normal force pushing upward, and we have frictional force going in the right-hand direction in this case. We're going to call that the positive x direction. I don't have, oh, yep, here's my coordinate system. So x is positive to the right, y is positive upward, and rotation is positive counterclockwise. So friction is in the positive I-hat direction. I've noted that if we're rolling, this contact point is I with a circle, meaning it's in an invariant or point of instantaneous zero velocity, just to remember that we have that relationship if we need it. So force sum, we have one force in the I-hat direction, and so it is going to be equal to the mass of the pipe per unit length times the acceleration of the center of mass in the x direction. So we have one force acceleration relationship. We can look at the fact that the pipe is not sinking down into the plate and it's not flying off the plate. So we know that the acceleration of the center of mass of the plate in the y direction is 0, which means that the normal force and the weight are the same, which also establishes a maximum available static friction, which will be important for maintaining our rolling so we don't ever have any slipping at this point. So, this is the most we can get from friction. And so that's what we will need to keep other effective needs for acceleration to maintain rolling below this criteria if we don't want it to slip. And we can express the sum of the moments about the center of mass of the pipe as r cross f. And in this case, r is in the negative j hat direction, f is in the positive I hat. So we end up getting a positive expression when we include the sign of the cross product. And we can equate that to our angular acceleration of the pipe and its moment of inertia. So we have three expressions. Acceleration of the center of mass, which is only in the x direction, so that's the entire translational acceleration related to frictional force. We have an expression of frictional force being constant, it's not changing in the problem, and we can also relate frictional force to radius mass of the pipe and our angular acceleration. So we got some relationships out of there. Now we FBD the plate, which we absolutely have to do to get at our applied force. We've got P in the positive I hat direction and F in the negative I hat, and then we have the weight, the normal force of the surface, and the normal force coming down from the pipe, all acting in the Y direction. The plate is not rising off the surface, it's not sinking into the surface, and so we know that the acceleration in the Y is 0, and so those forces sum to 0. So we really don't have any important equations in the Y direction. We know that the acceleration of the plate is all in the X direction. Let me grab a pencil. So all the plate acceleration is in the I hat, just like the entire acceleration of the center of mass of the pipe was also in the I hat. So nothing is moving or accelerating in the vertical direction. We can equate acceleration of the plate in the I hat direction with its mass. Remember, this isn't a moment, this is just big M for mass. So the mass of the plate times the acceleration of the plate is equal to the sum of the forces acting on the plate, which is P in the positive I hat and F in the negative I hat. So now we have an expression for acceleration of the plate in terms of forces and its mass. Okay. So we wanted to solve for force P in terms of no slip. So we need some expression for what does it mean not to slip. And then we need, inevitably, we'll probably need to relate all of these accelerations and forces that we don't know, all accelerations in this case. Now we have one force, F, because this is the max F that we need. That doesn't that we have available. It doesn't mean we will be utilizing all of it. So F is an unknown in this case. If it were already sliding, it would be fixed at this, and this would be a mu k. So we don't know F. We don't know any of the translational or rotational accelerations. Okay, so that adds up to the number of unknowns is our center of mass of the pipe, our frictional force, our rotational acceleration of the pipe, and the acceleration of the plate below it. So we have 4 unknowns. And how many equations? We have this equation coming out of the sum of the forces for the plate. We have this one coming from our Euler's second law application for the pipe. We have a max frictional force, but we don't know if we're using all of it, and we have friction related to acceleration of the center of mass. So 1, 2, 3 equations coming out of our force balance acceleration relationship. So we need one more, 4 equations and 4 unknowns. So to do that, we're going to take a look at that point of contact, and look at the fact that at any instant in time, the motion of that invariant point on the pipe translationally is going to be the same as the plate at that point. So the plate is moving over to the side, and that point of contact is moving with it. So if we include that, then we can relate, then we have our additional relationship that we need, and we reference that in terms of relative reference frames. So we can say that the acceleration of the center of mass of the pipe versus the surface that it's sitting on here, not versus to the plate, but versus the surface, is going to be equal to the acceleration of the plate versus the surface plus the acceleration of the pipe versus the plate. So basically any point on that pipe, we know how it moves versus the surface via the kinematics of rolling. We know the plate's accelerating across the surface because of single net force in the I-hat direction. But we have to put those two together to understand how the pipe is moving versus the surface. And that's going to help us get our last expression relating all of our unknown variables, and from which we're gonna get a relationship for P versus F using rolling criteria. So that's how we invoke the non-slipping. We write our expressions. We basically solve for equations of motion and relating our frictional force on our P using equations of motion that necessitate non-slipping, which is rolling, which is the pipe versus plate motion coming from rolling. So we end up with, if we use this relationship, which all equates to this, we can say that the acceleration of the pipe center of mass versus the surface is the acceleration of the plate versus the surface minus the motion, the translational motion of the pipe versus the plate. So that gives us our 4th equation. So we basically used relative reference frames. Now, typically, acceleration of the invariant point, if we're looking at it in rolling motion, it's vertical. It's actually normal back to the center center point. It only has a y-hat component, so it's only normal to the center. But in this case, that point is moving by the fact that the plate is moving. So we're basically looking at two bodies motion. So generally, no, certainly the acceleration of that point of zero velocity on a rolling body would generate, if we're only considering its acceleration relative to the rolling pipe itself, it's always going to be pointing backwards or pointing upwards towards the center of the rolling. But in this case, it has that component in the y direction because it's rolling. That's what's keeping it rolling in its trajectory on that rolling circle. But its I-hat component, I should say x, is only going to be due to the plate's movement, because the rolling motion itself does not give it an I-hat component. So that's really maybe a more correct and easy to understand way of saying it. That rolling doesn't give that invariant point any acceleration in the I-hat direction. It's purely in the normal direction, which is the J-hat in this case. So all of its I-hat motion is coming from the plate. So that allows us to link what's going on in the plate and what's going on in the pipe, and gives us this fourth equation. So if we solve these four equations and four unknowns, we can end up getting an expression for our pull force. P is a function of the frictional force. So we can get P equals F times 2 times the mass of the plate plus the mass of the pipe, all over the mass of the pipe. And if we include our onset of slip, max static friction of mg mu1, this becomes our maximum applied force to the plate to avoid slipping. So, quick review, important points we made. Probably the most esoteric point was using the nature of the invariant point of rolling and saying, I know what it's doing versus its own center of mass. I know what its acceleration is. It's only normal to the wheel. It's only pointing back towards the center of the rolling point. But it is relative to a different reference frame. It's translating. So that links what's going on the pipe to plate versus plate to surface, and gives us our fourth point. Other than that, what did we have? We had FBDs of the plate and FBD of the pipe. We included the relationship between moment of inertia and our rotational acceleration and net moment, sum of the moments. Nothing but sum of the forces coming out of the plates, and that was it. No fancy kinematics. We didn't even really have to break out any of the complicated kinematics of rolling in this case, other than to know that the center of mass was going to be moving translationally along the plate. Okay. Last but not least, pure rotation. So in this case, we've got a cylinder, and it has an initial angular velocity of 1,000 RPMs. It's clockwise, and there is this friction brake. We're looking at everything in cross section. So there's this angle arm, probably some kind of metal, probably kind of heavy and stiff, and we can apply an additional force to it. And we're going to use that brake to slow the rotating cylinder down and stop the rotation. We have a mass for the cylinder. We know it's a uniform cylinder, so we can get its moment of inertia with its radius and its mass. We've got some dimensions for the brake, and we've got a value of 40 newtons. And we're asked, when does the cylinder stop? When does it stop rotating if we apply that much force to the brake? X coordinate system, X is positive to the right and Y is positive downward, which means clockwise is positive rotation. And for reference, all of our omega, our angular velocity values, need to be in radians per second to go with our equations of motion, so we can equate that 1,000 RPMs to about 105 radians per second. So we'll use that as our initial velocity, which we'll need some expressions before we can get that. So we need to FBD the brake and the cylinder, and the thing that we need to connect them, of course, is this normal force and friction force. And we were probably given a mu k of 0.3. So what we really need is the frictional force, because that's in fact going to be the only force that is capable of applying a moment and therefore applying a negative angular acceleration and slowing the cylinder down. So we don't really have any translational motion in this case. So the trick becomes finding n and hence f out of our brake FBD. So this is back to statics. So we can do an FBD of the brake and basically look at the weights of each part and then the force. And we'll be taking a force sum in the y direction and summing the moments about this pivot point on the brake. And from that and knowing the value for P, we can get a value for N. And that's just using equilibrium analysis of our forces. And with our 0.3 mu K, we now have a force of friction of 13.3 newtons. And for these calculations, I've neglected the 2 centimeter brake width, so I've taken everything at the center of mass, and I've neglected the offsets for the actual angle iron. It's very small compared to the other dimensions, so these are approximate, but pretty close. So with F with a value for F, I can bring that down and use it in my cylinder FBD, where I find that it is in fact the sole force capable of producing a moment. I don't have any applied couples. So the sum of the moments about the center of mass of the cylinder at O is R cross F. So R is just the cylinder radius, which is in the negative j hat direction for the coordinate system I picked, and 13.3 newtons friction force in the negative I hat. So we end up getting a negative 2.66 newton meters, and that is the net moment. We looked up the moment of inertia about its center point of a cylinder, and again, if we use mass per or weight per unit length, or excuse me, mass per unit length, and we use a mass of pi r squared delta, that's per unit length of the cylinder, we end up with r squared m over 2, which when we put in our r is 0.2 meters and times 10 kilograms of cylinder mass. So we have our IZ, which we can use to get our alpha. So we have our minus 2.66 newton meters of moment, equaling our angular deceleration in this case times our value for IZ0, which ends up being 0.2 when we multiply all this out. And so we solve for alpha ends up being 13.3 radians per second squared, and we take the first time derivative, we get the velocity at any time. Angular velocity, when does the angular velocity equal 0? When we solve the line equation for t, and we get 7.87 seconds. So this is probably one of the simplest examples of application of our Euler's second law, moment of inertia, and some of the moments to a very simple equation of motion. We didn't have to worry about rolling criteria or slipping or coupling any kind of rotational motion and translational in this case. So this was much simpler, but something for which we absolutely needed to have that relationship between angular acceleration and moment of inertia with net moment. We really had to invoke our Euler's second law equation for rigid bodies in planar motion. So this is definitely a great example of something for which only that would give us a solution to the problem. So again, that concludes our discussions of rigid body planar motion kinetics. We've defined, in this chapter, we've defined angular momentum in terms of linear momentum and angular momentum of a center of mass. We've looked at how you can define angular momentum of a rigid body in terms of the velocity at one point, the mass of the body, and the angular velocity of the whole body, using properties of rigid bodies to relate those. We've taken the first time derivative of angular momentum, and we've looked at its relationship to inertial properties of a rigid body, looking at our expressions for angular momentum in terms of our product and polar moments of inertia, and then looked at which ones of those are non-zero for planar motion, and from that got our sum of the moments equals alpha times the polar moment of inertia, and then looked at ways we can leverage that along with other force balances and all of our kinematics that we've already studied for rigid bodies to write equations of motion based on of force balance and moment balance to solve for the net necessary acceleration. So next up will be work energy applications to rigid bodies, which will provide a lot of excellent simplifying assumptions, just like they did for our particle kinetics. So that will be our next section after this one. So stay tuned.